Whether it's record heat or a beautiful spring day, the weather around us is a huge part of our lives and a topic we're often eager to chat about. However, as important and interesting as the weather on Earth is, have you given much thought to the weather in space? Hi, I'm Dr. Sharon Petronella Crescent, Director of UTMB's Community Engagement Programming for the School of Public and Population Health. Welcome once again to Thought Leaders, the lecture series brought to you by Space Center Houston and proudly sponsored by UTMB Health. Today, we examine the influence of space weather on human health and technology. The sun is literally at the center of many things, including weather both on our home planet and in space. When scientists talk about space weather, it's a conversation about magnetic fields, radiation, particles, and matter that are ejected from the sun. These elements interact with Earth's upper atmosphere and surrounding magnetic field to produce a variety of effects, from disrupting technology to potentially impacting human health. We'll learn more on this fascinating subject from our expert panelists, Dr. Phil Chamberlain and Dr. Jari Collado Vega, who will help us to understand how activity on the surface of the sun, some 93 million miles from Earth, can distort radio communications, disrupt satellites, potentially harm astronauts traveling in space, or impact our neighborhood pool party. We at UTMB invite you to find a comfortable spot indoors, away from the heat, and join us in learning more about the phenomena of space weather. Thank you for joining us.
Hello, I'm William T. Harris, President and CEO of Space Center Houston. We are a nonprofit and an immersive space exploration learning destination with the purpose of bringing people and space closer together. We're also the official visitor center of NASA Johnson Space Center and help share the story of human spaceflight with more than 1.3 million visitors annually from around the world. Thank you for joining Space Center Houston's Thought Leader series, Space Weather, the Sun's Influence on Humans and Technology, presented by University of Texas Medical Branch. Our Thought Leader series brings you space and science experts from around the country to provide insights and perspectives on space exploration. NASA, partner government agencies, and commercial partners are focused on the Artemis program for lunar exploration. A critical part of our lunar research is informed by the findings and impact of solar reactions and space weather on our home planet. Our Thought Leaders topic discusses the significance of the sun and space weather, and how its influence has benefited and challenged humanity and technology. Here at Space Center Houston, we believe science learning and space exploration is for everyone, and are proud to celebrate 30 years as a hub of learning and as a point of pride for the Houston community and the space industry. We want you to be inspired through our immersive and authentic science learning exhibits and spacious outdoor exhibits. To get the most from your experience at Space Center Houston, purchase a time ticket online ahead of your visit to save on general admission. To plan your journey with us, go to spacecenter.org to review our Know Before You Go guide for additional tips on planning your visit and maximizing the fun. And now on with our panel, Space Weather, the Sun's Influence on Humans and Technology, presented by UTMB. We're excited to learn more about space weather and the impact it's had on human and technological innovation. In today's presentation, our experts will share new insights, lessons learned, and advancements that will provide insights about how the research is continuing to help power spaceflight. Our first panelist is Dr. Yaresca Collado Vega, who is director of the Moon to Mars Space Weather Analysis Office, which was established to support NASA's Space Radiation Analysis Group with human space exploration activities by providing novel capabilities to characterize the space radiation environment for the Artemis program. Dr. Collado Vega's research focuses on the solar-wind interaction with the Earth's magnetic environment, solar energetic particle events, and coronal mass ejections, X-ray imagers, and space weather effects on planetary environments. She also works on the validation of magnetospheric models and the current developments on machine learning capabilities to improve space weather analysis and forecasting. She's been part of the NASA family for almost 19 years and has worked on space weather analysis since 2012. Our second panelist is Dr. Philip Chamberlain, who is the Assistant Director for Science, Solar, and Stellar Group at the Laboratory for Atmospheric and Space Physics at the University of Colorado. His research is focused on measuring and modeling solar X-ray and ultraviolet of the sun. Dr. Chamberlain earned his doctorate in aerospace engineering sciences at the University of Colorado. While at the university, Dr. Chamberlain was a graduate research assistant at the University of Colorado Laboratory for Atmospheric and Space Physics, which led to a subsequent position at NASA Goddard Space Flight Center. He was with Goddard Space Flight Center for 8 years before returning to CU LASAP. Dr. Chamberlain is involved in every aspect of spaceflight instrument development, from conception to launch, and publishing the data analysis post-launch. Each of our panelists will now provide more information about their backgrounds and the scope of their work before we begin our conversation. We'll now hear from Dr. Collado Vega.
Thank you so much for the invitation. I'm really glad to be here. I'm going to talk to you a little bit more about my office, the Moon to Mars Space Weather Analysis Office. But first, I really want to talk to you a little bit more about what space weather is. So when we talk about space weather, we're talking about the conditions in space that are mostly dominated by the sun's activity. It is actually the study in terms of the application side of things of the whole heliophysics system or field. When we talk about space weather, we need to talk about different drivers. One of the main drivers are solar flares. When we talk about solar flares, we have to understand that they're very different than coronal mass ejections, and I'm going to explain why. A solar flare is an abrupt eruption of radiation, as you can see here from the SDO images that you're looking at. SDO is the Solar Dynamic Observatory. It's one of the highest resolution imagers that we use nowadays to look at the sun, to look at those active regions that create most of the activity as solar flares. When we look at these images from Solar Dynamic Observatory, or SDO, you can see that bright eruption of radiation, and that's actually the solar flare. This is actually a composite image that we use to actually see that brightening and see it in a way that we can actually understand that that's the source of that solar flare. The solar flare, like I said, is pretty much radiation across the whole spectrum, and it gets to Earth in about 8 minutes. Once it gets to Earth, it's already here. So this is one of the most difficult activities for us to predict, because we have to predict it before it actually happens, but we're working on it. Now, when you have a solar flare, what you can have in terms of effects on Earth are changes in the upper atmosphere, what we call the ionosphere, and you can actually have radar communication disruptions. So it's very important for us to understand how these events evolve and how we can actually predict them before they happen. Because, like I said, it takes 8 minutes to arrive to Earth. Now, when we analyze the solar flares, this is actually an event that I'm showing you that is kind of old, but if you look at the current events, so the sun right now is going towards the solar maximum. The sun has a solar cycle that is about 11 years. So in that 11 years, you go from a minimum to a maximum to a minimum. Right now, we're very close to that maximum. So that means that you get a lot of solar flares and also coronal mass ejections from those active regions. And you can see here, this is actually a day in July that we have only in one day 7 M-class flares. The flares have different classifications. It goes from A, B, C, M, and X, X being the highest classification. So M-class flares are not the most extreme, but they're pretty intense. And most of the time, they can actually be associated with a coronal mass ejection. However, they're not a one-to-one correspondence. Now, when we talk about CMEs, or coronal mass ejections, now we're talking about billions of particles leaving the solar corona. And depending on the speed of these particles, it takes about 2 to 4 days to arrive to Earth. The effects of that CME at Earth depend on the speed and also the magnetic field inside that coronal mass ejection. There can be a lot of interaction between the magnetic field coming from the sun, which travels with that coronal mass ejection, and the magnetic field from the Earth. The Earth has a magnetic field that actually shields us from this whole environment. And that interaction between magnetic fields can actually transfer a lot of energy, and it creates what we call the geomagnetic storms. When you have geomagnetic storms at Earth, that's when you can have situations like satellite drag, GPS scintillation. You can have power grid disruptions. So there's a lot of effects in the society that can happen because of this space weather events. What are you looking there are actually images, again, from the Solar Dynamic Observatory, which we look at in different wavelengths so you can see different temperatures. And that way you can actually see the sun in different layers to understand what's going on. Those are really nice eruptions of the coronal mass ejections. Now, SDO is great to see the sources, but when we talk about where it's going and what is going to impact, we need to block the sun to be able to see all those coronal mass ejections and where they're going. So now you're looking at SOHO, the Solar Heliospheric Observatory. It's actually a Lagrangian point 1 in front of between the Earth and the sun, looking straight to the sun. And you actually have to create an artificial eclipse. This is a coronagraph. This is what we're doing. The sun is too bright to let us see where that CME is going once it's already out of that initial region of the solar corona. Now, you see all those CMEs going all the different directions. And my team actually analyzes them in all different directions because we want to protect all the NASA missions across the whole solar system. But there's one that actually travels to the Earth environment, and you can see that rain of particles. That rain of white particles is actually the solar energetic particles. These are particles that are accelerated by these events. They're accelerated to fractions of the speed of light, and they're very energetic. These are the particles that can cause most of the damage to the instruments of the satellites in space and also create a hazardous environment to the astronauts. It creates the radiation environment that could be hazardous to the astronauts in space. So these are the solar energetic particles that we're trying to predict now for the Artemis program. We're going to the moon and then we're going to Mars. And to do this safely, we have to be able to predict these events coming from the sun. And it's not an easy task. Now, this is actually a visualization of a simulation initiated by real data. And this is actually showing the CME traveling through the space. And then when it arrives at Earth, you can actually see how those particles get shielded from that arrival, right? It's because we have the magnetic field here on Earth. It's actually our best shield of these particles. However, there's always transfer of energy and also transfer of particles. And this is actually what creates the geomagnetic storms that eventually creates the soft storms, and then you get the beautiful auroras in the northern, very high northern and lower latitudes. And this is because that's where the magnetic field of the Earth comes in, and that's where the particles, the particles actually follow that magnetic field line into the Earth environment. So auroras are beautiful, but I call them the rainbow space weather. But that means that we're pretty busy here because that means that the magnetic field of the Earth has been disturbed and the sun is causing that disruption to the magnetic field of the Earth. Now, when talking about my team, it's called the Moon to Mars Space Weather Analysis Office. We actually support Johnson Space Radiation Analysis Group with the human exploration side of things by providing new capabilities that could assess the radiation to protect the astronauts for the Artemis program. We also support NASA robotic missions with space weather assessments and anomaly analysis. When an anomaly happens, which actually happens after the fact, we actually help to see if space weather had anything to do with that anomaly. It helps into the development of new missions and also to understand the environment that the missions are in. We're working as proving grounds at a testbed for the capabilities that will eventually transition to the operational agencies. We work really closely with NOAA Space Weather Prediction Center, and the idea is for us to push the envelope all the time into those new capabilities, develop those new models that will eventually be used operationally by NOAA SWIPC and other operational agencies. Now, this is just to show you a little bit of our activities. We actually analyze real-time space weather activity 7 days a week. Now we do 8 a.m. to 4 p.m. However, that's going to change soon because the sun is really active. However, when we actually do mission critical like Artemis, we are 24/7, and we were 24/7 for the 25.5 days that the Artemis 1 mission was actually orbiting the moon. So that was pretty exciting. We send notifications to the NASA missions, and that's actually an internal NASA list. And it's actually an analysis on all events on all directions. And that's why it's so important to us to also have observatories along the whole 360 degrees of the sun, because we need to be able to see the sources and where those CMEs go to actually understand the impact that could actually cause to the missions out there in the solar system. We have to protect our NASA missions. Now we document and archive everything in a database called Donkey, the space weather database of notifications, knowledge, and information. Down there in the bottom of the slide, you have a lot of tools that we use that actually go with our collaboration with the Community Coordinated Modeling Center, CCMC. CCMC develops the tools, and my team is the one that populates the tools with the real-time analysis. Now, the database in Donkey has pretty much everything that has happened in the space weather environment from 2010 forward, and we actually populate it in real time. And we link everything to each other. So if we have a solar flare that was associated with that coronal mass ejection, we have that linked in Donkey. We support, like I said, anomaly analysis for NASA robotic missions. We're part of the Mission Resilience Program here at Goddard. And we support information also for NASA payloads for launch activity. And we did this for the James Webb Space Telescope. We're very proud of that. Now, this is an example on how my team analyzes those coronal mass ejections. So you see the source. One of the things that is really important to understand, sometimes there's not a one-to-one correspondence between solar flares and coronal mass ejections. However, it is true that when you have most intense flares, usually they come associated with a big eruption and a CME like this. When that happens, you know the source, you know where the CME is actually originated from, then you know a little bit on how locate those parameters, which ones are the longitude and latitude. And then we use tools like the one that you see here, the IDL SWIPSICAT, that actually uses triangulations to actually understand and parameterize the 3D velocity of that CME. When we get that, we actually can see the parameters and we ingest the parameters into the database. Now, here is one of the examples that you can see here. This is an event that actually happened in June, this past June. And you can see there the velocity, the catalog that was used, the longitude, latitude, the half width. These are all parameters that I needed to run a simulation and then have a prediction on when and where this CME is going to impact. This is that simulation run by those parameters. So you can see here in the center is the sun. This is the WSA Enlow plus Cone model. It's a mouthful, but it's because there's 3 models into one. So the WSA is actually describing the magnetic field of the sun. Enlow is the part that propagates that magnetic field to the heliosphere. So it's the one that creates that background. And then the cone is actually the CME being ejected that you see there. Now you have the sun in the circle, the sun rotates, so you can see that spiral going around. And then here you're looking at density. Density is what this is describing in this color, okay? Now you see that CME being ejected, the circles are the planets, the squares are the missions. And with this, we get an idea on where this CME is going to impact and also when. And with that, we send that notification out to the mission so they know to be prepared for something like this. And in this case, we're actually impacting Venus, a glancing blow to stereo ahead, and also Mars, where we have the MAVEN mission. A very important part of our group and how this is all started is about the ICEP collaboration. It's the Integrated Solar Energetic Particle Warning System. It's a collaboration that started with the Community Coordinated Modeling Center, CCMC, and NASA SRAG. I was part of CCMC when this all started, and the idea was to transition solar energetic particle models from the research community into operations. The CCMC did an amazing job into creating the CP scoreboard, which you have on the left, the intensity scoreboard, and then on the right, you have the probability scoreboard. Depending on the models that you use, you have different outputs. Some will give you a probability of an event happening. Some will give you a peak intensity or a profile of that event. What we do is understand the models in real time, validate the models in real time, and then compare, doing a comparison of that output and forecast of the model with the real data from the GOES and also from the SOHO satellites. This is an amazing tool that SRAG is already using for the International Space Station operationally. And we also used it with SRAG for the Artemis 1 mission, and we're actually preparing now for the Artemis 2 mission, where we will have aboard the 4 astronauts that were chosen. We do a lot of collaboration, which is one of the main activities of the team, and we love all these collaborations that we have. Our main mission collaborations are, like I said, the CCMC, NASA SRAG, and also NOAA SWIPSI. But we also work with many missions like Parker Solar Probe, Solar Orbiter, Mars Curiosity, James Webb, Juno, and MAVEN. We work really close with them, and some of these missions actually use our analysis and notifications to create their own database specific for their mission. We have a very strong collaboration with MAVEN, CCMC, and us, and the idea is to develop data and tools dedicated to the Mars environment. Artemis is not only about going to the moon, we're going to Mars, and we need to start now to prepare for that. We cannot wait. So this is my summary. Our office will continue to conduct and provide model-based predictions and analysis as proving grounds and tool development in support of NASA SRAG. We're focusing our efforts now in the Artemis 2 mission, which is coming in 2024. We have a very strong collaboration with CCMC, forming a NASA in-house R2O2R pipeline, which means research to operations, operations to research. And we have a very strong collaboration with NOAA Space Weather Prediction Center. We also support NASA robotic missions with coronal mass ejection modeling efforts, space weather environmental assessments, and anomaly analysis support. And we work really closely, like I said, with many missions, James Webb, Parker Solar Probe, Solar Orbiter, OSIRIS-REx, and MAVEN, because that's the idea. We need to make sure that we get all the data that is out there available for us to do our mission and to do it how we need to do it. We're always looking to push forward the envelope to do new research developments. And we're already working with other missions and groups to validate, like I said, predictions at other locations, different locations that is not the Earth environment, for example, the Mars environment. And we do that amazingly with the MAVEN mission. This is my team. I'm very proud of them. They work really, really hard every day to make sure that NASA missions are safe, that they have the information that they need in terms of the space weather environment, and we're always looking forward to more collaborations. Thank you so much.
Thank you, Yadi. That was fascinating. I have so many questions for you. I can't wait for our discussion section, but that was a fantastic orientation to the sun and its impact on Earth and our entire solar system. Now we're going to hear from Philip, and then we'll begin our discussion.
Thank you very much. That was an awesome overview of space weather, the effects, obviously some great movies that we got to see and Dr. Collado Vega showed. And it makes my job easier because now I can get into stuff that I do with this great introduction. So I appreciate the chance to be here and talk to you about space weather and how I fit into this larger picture. So what I do is I study how the sun varies on all time scales, not just the space weather time scales. You see another beautiful movie down there in the lower left corner that shows the sun rotating and the active region rotation that happens with the sun just spinning on its axis. And these active regions appearing on the limb, disappearing off the limb, growing, disappearing just in themselves, but also some more wonderful flares that are going off there, these large energetic eruptions. But moving back, the sun also varies on longer time scales. The sun has, as was mentioned by our previous speaker, an approximately 11-year solar cycle where it waxes and wanes in brightness, especially in the UV, as well as in the frequency of these large-scale solar flare activities and coronal mass ejections. So you can see a beautiful composite that's put together in the upper left, looking at extreme ultraviolet light, this one that's around 17 nanometers in wavelength. And you see from solar min, it's kind of dark, void of all these really bright spots called active regions. And you see how it grows and it becomes more active. And there's more eruptions, more solar flares, more CMEs that come onto the sun. And then they go and they wane back down to a quiet period. And then they grow again. Sometimes these the solar cycle could last 8 years. on some of the fastest cycles up and down, but sometimes they could last up to 13 or 14 years. That actually happened on the previous solar cycle. Everybody was like, what happened to the sun? Did the sun die? Where did the sun go? Is it ever going to wake up again and go towards this maximum period? And of course it did, as it has since we've been monitoring it, monitoring the solar cycle. And so I study how the sun's output varies on all these timescales from years to decades, down to how it varies on the orders of seconds for these solar flares. And then as the previous speaker got into, absolutely wonderfully, is how does it really affect us on Earth? I'm a scientist, I'm an engineer, and I love studying things, specifically for a science point of view. How does this vary? Why does a solar flare occur? What are the physics going on? What are the nuances that are going on the sun to actually trigger this flare and make it erupt? And then how it propagates to Earth and how it affects our ionosphere and our thermosphere, these upper layers of the Earth's atmosphere that are driven by the sun's activity, especially the ultraviolet wavelengths of the sun. But then I'm also very interested in, this is very applicable to us as humans. It impacts not only the technology itself, such as solar panel degradation. The satellites that rely on solar panels to provide them power out in space degrade over time with these particles hitting them. And so their ability to produce the power they need to operate degrades over time, as well as astronauts being exposed to radiation, even airline and passengers on airlines, especially as they go over the poles, where they're impacted by the radiation that comes in from the magnetic field in the North and South Pole. As this radiation from the sun comes in, gets protected by and blocked by our magnetic field, but eventually makes its way into the North and South Pole. If you're flying from the US to China, US to India, sometimes you go over the poles and you could really be susceptible to the radiation that comes in the poles, especially if you're a pilot or a flight attendant and you do that regularly. The dose accumulation could be significant and influence you. But then there's all sorts of other things. GPS, we are very dependent on GPS. That's probably one of the things that's most affected. Some of the big shipping container vessels that you see that are loaded down, they have so much cargo, these cargo boxes stacked on them, that sometimes they come, feet from the bottom of the ocean, and they're navigating via GPS. And if a solar flare goes off, it could affect the ionosphere and thermosphere, and therefore it could affect GPS, and therefore your position that you get using GPS could go from an accuracy of inches during quiet times, but they actually tell you, and you could now be feet off or tens of feet away from where you are if a solar flare is going off. And if you're shipping containers loaded so much that you're just barely scraping the ground and just navigating, but all of a sudden you're tens of feet off, you could run aground. And so there's serious impacts on that, as well as surveyors that are using GPS to get their position when they're making buildings and surveying land. There's all sorts of applications for GPS and radio communication. And so this is what I do. I'm on the experimental side of things. I like to build the instruments that make a lot of the measurements that have been shown, and how we study the sun, and we get the inputs on how the sun varies. So there is there's a range of instruments, and as you can see on the left, this is sort of like the very simple, cheap way of doing things. They're called sounding rockets, NASA sounding rockets. So these rockets are about 60 feet tall. There's science payloads in there. This one's being launched from White Sands Missile Range down in New Mexico, and these have solid boosters, and they just get up and go. They're reaching the speed of sound by the time the tail hits the end of the rail. That's how fast these things take off. But they're called sounding rockets because they go up into space, get above the Earth's atmosphere, get up to about 150 miles peak altitude. We get about 5 minutes of data looking at the sun, or other things. Sounding rockets look at the ionosphere, they launch into auroras. There's lots of cool things you could do with the sounding rocks, but we look at the sun with the ones that I'm involved with, and we get about 5 good minutes of data, and that's all we need to do the science that we need to do. And we also prove new technologies on these sounding rockets, say, hey, this survived launch, this survived space, this looked at the sun. And then they'd come back down on a parachute about 150 miles downrange, and we go pick them up in military helicopters, bring them back, and we could dust them off and launch them again. So they're pretty fun. So that's kind of like the quick, cheap, short version. But this now shows a lot of the instruments that I work on. So I've been involved in, so that's actually the top left one is actually the guts, the inside of what was in that sounding rocket that just went off. But I've worked on a lot of other instruments as well. A lot of these are purposely meant to study the sun and study the solar variations in terms of solar flares, solar rotation, and solar cycle, and really track the waxing and waning of the sun, the increase in activity and the decrease in activity. And there are lots of different platforms, from sounding rockets to instruments on almost billion-dollar missions, instruments that are going different places in the sun, to also CubeSats. CubeSats are these little bread box type things that you could get a lot of science out of for fairly cheap. But you see right there in the middle, there's also a little instrument that we call EUVM on the MAVEN spacecraft. And what this is doing is it's essentially monitoring the sun from Mars. So we could do space weather at Mars too. The sun's influence, it doesn't just influence the Earth. It doesn't just impact the Earth and the technology at Earth. It impacts the entire heliosphere. It impacts all the assets that we have, except for 2, the Voyager ones that actually left the heliosphere and are no longer impacted by the sun within our heliosphere. But everything within that bounds is influenced by the sun. And as I mentioned, we went to Mars. We're looking at the sun from Mars. And the whole point of doing the MAVEN mission is to look at the sun and its influence on the Martian atmosphere in present day to say, if a solar flare goes off, how much of the atmosphere is stripped away? How much of the atmosphere is lost due to the solar cycle, just due to the constant sun coming in, during a solar flare, during a CME? How do all of these solar variations influence the loss of the Martian atmosphere today? And by accurately quantifying it, not just with their solar observing instruments, MAVEN also has a great, impressive suite of instruments that study and look at the Martian atmosphere directly, and look at its loss, and look at not just the sun's particles and photons coming in, but also the atmosphere going out real time. So MAVEN was meant to look at climate timescales. Look at what we're doing right now and extrapolate this back 1 to 2 to 3 billion years ago and say, could Mars have ever had a thick enough atmosphere suitable to have water and maintain liquid water on the surface of Mars, which you see an artist's description or right there in the middle. You see the small blue marble, and artist's rendition of what Mars could have looked like if it had a thick enough atmosphere to sustain liquid water on its surface, and therefore where there's water, there's probably life. So it's an exciting mission. It's different than a lot of the rovers that are on the surface of Mars looking for direct details of gullies or evidence of water, or looking at different sedimentary layers or flows of water directly. We're looking at the atmosphere and say, could Mars have ever had an atmosphere to support liquid water and life in the past? But it ends up being one of the best space weather monitors we have, not only because of all of this great solar observing instruments we have on it, but also in situ instruments that are there sitting in the atmosphere of Mars, saying how much of the Mars atmosphere is being lost currently due to this variation in activity. How does a large solar flare increase the loss of the Martian atmosphere? So it's one of our best space weather observatories, looking at all these space weather events. And that's important because we're also not just looking at it from Earth. As these movies showed and the models that our previous speaker showed, these aren't just things that come directly at Earth. These are spread out throughout the heliosphere. And having our assets here at Earth, as well as assets looking at the sun from a different vantage point, sometimes will give us a 3D view or a different buoy in the water. If you're, say, looking at hurricanes, it gives us 2 vantage points to look at an event, and we can look at the 3D nature of these events, not just one little single vantage point. So MAVEN has been absolutely wonderful as a space weather asset. Even though it is a planetary mission in the planetary division, we're doing some great science. And we're not only looking at the science right now, how does solar variations influence the Martian atmosphere, but we're also looking at the space weather aspects, meaning the technological influence. Does this affect our spacecraft? Being further away, what does that extra distance help save us a little bit more? When humans start going to Mars, which I'm very excited about, and there's lots of potential that this is actually going to happen, how do we protect them? We don't want this to be a one-way journey. We want to get the humans there. We want to keep them there. We want them to be safe. And MAVEN is paving the way to make those measurements, along with a lot of other suite of instruments that are at Mars right now, to say, what do we have to do? What is the environment there? How do we have to protect them? What is the influence of the sun? What can we do to keep our astronauts safe? And so that's very important, and MAVEN is laying that groundwork. And so this is just a couple quick little views of the instruments. This is the extreme ultraviolet monitor on MAVEN. Again, this is about the size of the animal cracker box that you see. It's just 3 little eyes on the sun, essentially. And you can see 2 of those plotted here that just basically shows a solar flare that happened on September 17th of 2017. It just shows that we're looking at the sun and we see a big flare. We see a big spike in the energy, in the photons coming in from the sun. And of course, there are 2 different ones. We're looking at 2 different layers of the sun, similar to 2 different colors of the images that were shown from SDO. And you see that there's big spikes. And we as scientists could learn a lot about this. We could quantify the amount of energy coming in, which is very important. Not just say, I see a spike, but you see the actual irradiance numbers, the milliwatts per meter squared per nanometer there. So we could quantify the energy input in the atmosphere to do the science, do the space weather, to do the influence on technology. And then another complementary instrument on MAVEN is the IUVS, or the Imaging Ultraviolet Spectrograph. And so this is the instrument that's actually looking at Mars, looking at the Martian atmosphere, and seeing how it changes due to the changes in solar activity. And this is a really cool artist, or this is actual data from IUVS that shows on the left before a solar storm occurred, and on the right, once the high energy particles slammed into Mars. And you could see these are actually aurora on Mars. These are actually the atmosphere of Mars being lit up by the impact of increased high energetic particles from the sun. And what you see is there's a little difference there. Mars is dominated by its crustal magnetic field. It does not have the strong north-south dipole magnetic field that the Earth does. So we don't get on Mars, we don't get auroras in the northern hemisphere and the southern hemisphere exactly as they were on Earth. But when particles come in, these high energy particles, they light up the sun-facing side of Mars. So we actually see the impacts of a huge solar storm event impacting Mars and lighting up the sun-facing side of the Martian atmosphere. And so just who I am, I like to call myself a space weather scientist. I don't just study the sun. I don't just study the Earth's atmosphere. I don't just study Mars, but it really is a system science. It really is a coupled set. You can't just study the sun. You can't just study the Mars and understand the influence of the drivers and the influence and then the response on technology. It is all coupled. So I like to call myself a space weather scientist, not just a heliophysicist or a planetary science or an Earth scientist or whatever. It's the system science. And it's not just looking at the cause and effect from a science point of view. Sun brightens up, heats up the Earth's atmosphere, but really expanding into the impacts that it has on technologies that we are becoming more and more dependent upon, especially once we go outside of our protected magnetosphere, our protected magnetic field that we love to live in here at Earth. When we go back to the moon, continue to go send humans to the moon. When we go to Mars, we need to know how to protect them once they're outside, this force field, the Earth's magnetic field that we live in today. So that's who I am, and I look forward to having a wonderful conversation now.
Philip, thank you so much. This has been an absolutely fascinating presentation. I've learned so much already from both of you. And for our viewers, maybe I want to step back for a second and have you say, what is the sun composed of? And how is it that the sun has an axis? I didn't even realize the sun actually goes through this 11-year cycle of heating up and cooling down and heating up and cooling down. So what is the sun composed of, and what causes the flares to happen?
That's an absolutely wonderful question, and it could really go back to your periodic table. If you ever remember your periodic table, it's mostly hydrogen. It's a whole bunch of hydrogen. But one of the big things about it that really gets to the root of your activity is it's an ionized plasma ball. Plasma means it's so hot that you're actually in a state where you strip off your electrons from your atom. So it's a bunch of charged gas. And the fact that it's rotating, it rotates on about a 27-day rotation cycle. And it's that motion that was formed when the whole solar system came in. That's why the planets rotate. It's all a conservation of energy, that when all this stuff came together, it came together and it started spinning. But it's that spinning motion of a plasma ball that really starts to make things happen, to make things move, to make things go around. And what happens in the plasma is it likes to take the magnetic field that's there. You know, like the North and South Pole, the magnetic field that we have at Earth is actually kind of bundled up and concentrated due to the fact that the sun is rotating. It concentrates this magnetic field into these flux tubes. And so therefore you get these really strong magnetic field lines that you see in these beautiful SDO AIA images that really builds up this energy. And once these flux tubes are there, they want to continue to move and continue to impart energy and build up this energy. But just like earthquakes here at Earth, once you get to a critical point, you build up so much energy that you have to suddenly release this energy. And so this energy is suddenly released of this really built up concentrated magnetic field, and it just wants to release. But you can't just get rid of energy. You can't just get rid of it. It all turns into heat, it accelerates particles, and that's what happens in a solar flare or a coronal mass ejection. It's a sudden release of all this buildup of energy from motion and charged particles.
Not only that, that's actually a great description, but the sun doesn't rotate uniformly. You know, the equator rotates differently than it does in the poles. And that actually rotation can actually be used to describe the changes in that whole dynamo and the magnetic field changes between the solar maximum and the solar minimum. However, the solar cycle is something that is not completely well understood. And we can see that with the prediction of the current solar cycle 25, where the prediction that was official is much less than the actual activity of the sun at this current time. So the sun is already way more, it's more high in activity than it was actually predicted to be. And it's because of that. It's a very difficult aspect of the heliophysics, the solar physics fields to understand. And that's why we need more observatories. And we have, for example, Parker Solar Probe, which is one of the missions that we use to understand in situ what's going on, because it's actually going really close to the solar corona to understand that environment, because most of the data that we have from the sun is remote. And that doesn't help, because we actually can create the theories, but then we're like, okay, can we get that data? And Parker Solar Probe and also Solar Orbiter are missions that are helping us to get those data sets that are needed to improve those models that use that theory and then say, yes, is the theory correct or not?
That is so confusing in a way to create prediction models if it's always dynamic and changing. And how fascinating that, you know, being a, if you will, a big liquid hydrogen ball, it's very dynamic, right? Because it's something fluid, and so it's not like a mass that's rotating on its axis, right? It has different motions that happen, so it makes it even more complicated to predict its models. So when a solar flare happens, let's say we're launching Artemis 2 with astronauts, and we didn't predict a flare, but one occurs, and often a mission from Earth to the moon is about 3 days. and a flare can get to Earth in 2 days. And so what is the possible consequence for a mission if they are in transit and they're leaving the protective magnetic field of Earth and a flare is passing through the solar system?
That's a great question, and we need a clarification. A solar flare gets to Earth in 8 minutes, right? That's actually radiation across the whole spectrum. We actually measure it in X-rays. It gets here in 8 minutes. Now, a coronal mass ejection, those are the billions of particles being ejected from the solar corona. That's the CME. That's the one that will take 2 to 4 days. Even though that those are the timescales of those events, that's not what is actually really important for the astronauts. What is important is what can be caused by the solar flare and or the CME. Those events sometimes accelerate solar energetic particles. They're high energy particles that are accelerated as fractions of the speed of light. Those are the particles that can be dangerous to the astronauts. Right now, we have astronauts in the International Space Station, right? But they're protected from most of the energies of those particles because they're inside the magnetic field of the Earth. They're in LEO orbit, low Earth orbit. Because of that, we actually are very worried about them when we have a very high energetic event. But now we're talking about getting away of that magnetic field of the Earth. We're getting away of that shield. So now we have to care about all the energies because it doesn't matter what the energy is, it could actually penetrate. The higher the energy, the more penetration it costs, right? More penetration can actually happen. And there's already concept of operations on what the astronauts need to do. And that's what my team is trying to do. We're trying to develop models that can give you a better lead time or warning time. So we can actually tell the astronauts, go into shelter, there's an event happening, and they can actually be safe from those events. So that's what my team is trying to do right now.
So how would an astronaut shelter him or herself? Would it be in an area of a capsular vehicle that has some type of insulation? Or I know we here have at Space Center Houston, the AstroRad vest, which is a technology being developed in partnership between AstroRad and Lockheed Martin, right? It's a vest that protects the internal organs. Would it be putting on some type of protective clothing?
That's a great question. One thing that I wanted to point out is like the particles that we're talking about, the timeline is about, it could be 30 minutes, 2 hours, okay? So the best lead time that we can actually have, and we hope to have, is about 30 minutes. And the astronauts will actually go to one of the places, for example, in the Orion capsule, there's a specific place under the bottom side of the capsule where they actually go and they put everything that they have in the capsule on top of them. There's actually a video online that actually shows this from the NASA Johnson Space Center. And they actually say that it's about 30 minutes for them to actually do that. So there's ways of protecting the astronauts. It's just that we need to make sure that the communication goes in time for them to do it and take action. Talking about the Orion capsule for Artemis 1, for example, Artemis 1 was very important because we wanted to study and understand the radiation environment. And there were actually instruments in the capsule that were actually measuring that radiation. And they were in different places of the capsule. We had ones that were very close to the wall on the outside. We had ones that were on the inside of the capsule. And then we had one that it was on that shelter place. And with that information, we can actually say how much protection the astronauts are getting inside that capsule. Not only that, the Artemis 1 had also, the dosimeters trying to understand the radiation inside the tissue. And the idea is for us to understand exactly that, like how much radiation they're getting out there in space. Unfortunately, we didn't have a solar energetic particle for Artemis 1 while it was actually orbiting the moon, but we did go through the Van Allen belts. And this is a very, high radiation place, and we do have that data.
That's absolutely fascinating. So I have a question about, and this might be more for you, Philip, because there's also cosmic radiation, right? So there's other radiation in the solar system or passes through it. And so Are you monitoring that for human missions or looking at that? Because is it a combination of solar radiation or the CMEs along with cosmic, which is coming from some other source?
Yeah, so the interesting thing about cosmic radiation is from outside the heliosphere. It's from all the other things that are out there that is coming in. And so the interesting thing about that is it's anti-correlated with the solar cycle. So the stronger the solar cycle is, the more it pushes out the heliopause, the more density's out there, and the cosmic radiation actually decreases. So in terms of the cosmic radiation and its influence on astronauts, the best time to launch is actually during solar maximum. for that reason, it's anti-correlated. It goes out of phase because the sun actually helps block, an active sun helps block the extragalactical cosmic radiation that's coming in. But those doses are not nearly as much as you can get right on from a solar energetic particle event. Just being so close, having a much higher density. So it's those solar energetic particle events that we really need to worry about. And as we mentioned, those are more frequent during solar maximum.
So the GCRs, galactic cosmic rays, are really, really important for human exploration. There's actually a lot into studying the effects of GCRs. And like Phil said, yes, when it will be ideally for us to launch the mission where we're in solar maximum, so that activity from the sun creates like a shield of the outside particles that are coming from the outside sources, from the outside stars of our solar system. So, but there's a lot that comes into when we're launching, what's going on with the mission. So unfortunately, it's not the main factor that we have to take into consideration when we're launching. However, we're working on understanding the GCR flux changes and also how we can predict, like Phil said, those SEP particles that are coming from the sun. Because yes, you launch during solar maximum, you get better shielding, but then what happens with those events that come from our own star? That's why we're trying to work with all this research community into getting all those models that could be used in real time to get a better lead time of those events. And we're getting there, but there's definitely a lot more to do.
So of course, Artemis is NASA's top priority right now as we are developing models and preparing to become an interplanetary species. And one of the big goals of the Artemis program is one, of course, having the space platform, where this architecture is launching from Earth to the platform, which will be in orbit around the moon, right? And it's going out pretty far from the moon. So you're getting farther away from any protection from Earth, but then also creating habitats on the South Pole where astronauts will live for a period of time. Are you in your research looking at how we protect astronauts living on the surface of the moon? Will they need to create shelters that protect them from radiation because the moon really has no atmosphere?
There's a lot of moving parts now for the Artemis program. NASA, for example, just released the Moon to Mars architecture document. And the focus of that document is the moon environment. And the idea now is, like you said, understand how the humans can actually go to the moon, but not only going there, but staying there. It's a sustainable presence on the moon. And there's a lot of research. We're also trying to work with missions that could help us understand that environment before we even go and set boots on the moon. And we also have, for example, the plan of the Gateway, which will be orbiting the moon like the ISS does the Earth, but now the Gateway will be orbiting the moon. And the idea is to have also suites there of suites of instruments that could actually measure the radiation environment, so we can know exactly how that radiation environment changes nearby that cislunar system. So there's a lot of moving parts at this point within the NASA community.
Yeah, so from my point of view, being an observational and instrumentation person, is getting the information to know that there's a space weather event occurring. It's important to react to it and get your mitigation strategies. But right now, I mean, moon is all right because that's not that far off from the Earth-based resources we have observing the sun. But if we go to Mars, and when we go to Mars, MAVEN is not likely going to be there anymore, is we need a distributed set of things looking at the sun to be able to react, to say, hey, there is an event going off. There's no point in having a shelter or having all these mitigation strategies in place if you don't even know what you're reacting to. So MAVEN is great right now, but we need the assets out there monitoring the sun, and having and developing not just the physics of what happens, because understanding the physics of a flare and the physics of a CME will then lead to prediction. You can't predict something if you don't understand what's going on. So we need to, one, understand the physics of these eruptions so that we could predict better when they're going to happen. But then we also need the monitoring assets and the observational capability to say this stuff is happening on the sun and is going to influence you on Mars as real time as possible and with as much lead time as possible, so that we can even react. And that's the important thing, because when Mars is on the far side, when our astronauts on Mars are on the far side of the sun, and MAVEN is gone, we won't have anything to even let them know right now what's going on. So that's what's important to me, is developing the observational capability, knowing it's hand in hand. You can't send astronauts to Mars without having the monitoring and the knowledge to know what is needed to keep them safe.
Following on what Phil was saying, yes, it's definitely very important for us to have the observational capabilities, especially on the backside of the sun. Right now, for example, my team works to pretty much protect the missions out there, and the missions sometimes are in the backside of the sun. And right now, we only see the Earth facing this, even from, in the UV images that I showed you, or even the coronagraph images that I showed you, we're only seeing the Earth facing this. So when we have something happening on the backside, it's very difficult for us to say exactly the source location of that event. And that makes it very difficult, because it actually increases the uncertainty on the measurement and the simulation that we actually use for predictions. So we definitely need to move away of that sun Earth line, not only, like Phil said, to go to Mars, but also to understand the whole environment within the whole solar system. We need to protect our assets, and the only way to do that is to get the data for us to be able to do it.
So one of the great things we have coming up is mainly led by ESA, the European Space Agency, but NASA has an instrument that is going to go on, and it's called the Vigil instrument, or the Vigil spacecraft, and it's going to launch around 2027, 2028. But it's a space weather mission, and it's going to go to the Earth-Sun Lagrange 5 point. So it's basically 60 degrees away from the Earth. And what it does is it's peering behind and over the limb of the sun. So as the sun's rotating, it's going to be able to see with 4.5-day warning what's coming around the limb that we can't see right now. So it's going to be a really cool, it has instruments on it to monitor the chronograph. NASA's providing the EUV imager, similar to these beautiful movies that you saw from AIA. It'll be able to determine the magnetic field of the surface of the sun, and then we'll be able to track CMEs from the start, from the surface, do the solar atmosphere through the UV imager, and then do what's called heliospheric imagers and chronographs to then track it and be able to track it. And from that viewpoint, you get kind of a profile view of a CME that's leaving the sun and impacting Earth from the surface of the sun all the way to Earth. And so you're going to be able to track this, looking at it from the side, as well as just being able to peer 4.5 days in advance of the sun, that what's coming around and rotating on the face of the Earth. So that's a really cool distributed architecture that we're talking about, not just having asset at Mars, but having assets at L5. And then on the other side, at the L4 point that's in the front, that there's reasons you want to look at that, to look at a Parker spiral or look at SEPs, and having these distributed 3D, multi-vantage point views of the sun will really help us understand the physics of these events, as well as give us warning on what's coming to us at Earth, and for those astronauts that are on the Lunar Gateway and Artemis and all these other assets outside of the protective Earth's magnetosphere.
Wow, that is absolutely amazing. I cannot wait for that mission, because that's going to provide a whole new perspective and incredible new information. Speaking of Mars, I want to pivot to MAVEN, because it's absolutely fascinating that we've had MAVEN observing Mars over the years. Do we have any sense of why Mars is losing its atmosphere and at what rate from the observation? My understanding was, of course, it's particles hitting the atmosphere of Mars, but also Mars perhaps is losing its magnetic core. What are the causes of Mars' atmosphere peeling away? Do we have a sense of that?
The main reason it is the sun is just continuing to bombard it. It doesn't have the magnetic field that the Earth has to sort of protect us from this heavy bombardment and provide some sort of shielding. It doesn't have the big magnetic field to protect us. It does have an atmosphere. There is a bow shock of deflection of these particles around it. But what happens is the solar UV irradiance, the photons come in and they puff up the atmosphere. They energize the atmosphere a little bit, and then the charged particles from the CME or the solar wind or SEPs come up, and then they strip off this atmosphere that's then puffed up. And it's a lot more complicated than that. There's having to do with the Mars is rotating itself. There's escape processes that come up. The dust storms also provide some energy. It's a very complicated diagram of the interrelated processes. But the fact is that this Martian atmosphere is continually being stripped off faster than it's being replenished from below. And previously, when you get to look at the early sun rotated faster. And because it rotated faster, there was actually more active regions, larger active regions, more solar flares, larger solar flares, more coronal mass ejections and larger coronal mass ejections. So if you take the sun and you look at stellar analogs or stars that are similar in properties to the sun, but earlier in their age, you can tell that they are more active and there are more and larger flares. And so Mars early on was being bombarded by a much more active sun and had a lot more energy input into it and a lot more stripping of the Martian atmosphere that's occurring over time. So it's a simple math problem. If your replenishing of the Martian atmosphere is greater than the loss, then you're going to build up a thick atmosphere. But right now, and especially early on, the loss of the Martian atmosphere has been more than the replenishing. And so that is exactly what you're talking about, is the MAVEN mission has actually quantified the loss per constituent. We're looking at individual species of the Martian atmosphere and looking at their loss rate over the life of its mission, and looking how those loss rates of the individual constituents in the Martian atmosphere and how their loss rate depends on solar activity from their irradiance, from the UV irradiance, from CMEs and the solar wind and all of the other inputs, and looking at the loss mechanisms and modeling these loss mechanisms. So it is a very complicated process of lots of different processes, but it's a great team of about 60 scientists, international scientists. They're all coming in and doing their part of this complicated system and trying to all come together to provide a comprehensive picture and quantification, actually getting numbers and loss rates down of how the Martian atmosphere is currently being lost and depleted.
So there have been suggestions that somehow or over time there might be a way that we could help replenish some of the Mars atmosphere. Is that a total pipe dream? Is there really science that supports that could happen? One thing I wonder about is the sun as a gaseous body expanding or contracting, and could that affect whether or not Mars could reestablish a greater atmosphere?
That is an absolutely wonderful question, and I believe one of the prominent figures with SpaceX and now Twitter has very much been in the forefront of popularizing this idea that we could terraform or Martian form the atmosphere back on Mars. And the original principal investigator of the MAVEN spacecraft, Dr. Bruce Jakosky here at LASP, it's one of those things that you could just get him started. If you even mention that, you could just see him starting to boil and just be like, not again, I don't want to answer this again. So Dr. Bruce Jakosky has a lot of popular opinion pieces out there in the media, has done interviews, and just saying that no way is essentially his answer. We are so far off from being able to provide any method of terraforming and providing a thick enough atmosphere that we could potentially end up getting surface water back on Mars and make it habitable again. That it's so far off that it is impossible.
Well, that's absolutely fascinating, because I think that's one of our purposes here, is to really present the science to the public, to recognize what research tells us or suggests to us, based on theories. And of course, it is important to dream, and that's how we lead to exploring things and asking questions and trying to verify or determine if they're true or not. So that's fascinating. Well, of course, our sun is an absolutely amazing gaseous body, right? Because it's, holding in place all of these planets and the asteroid belt and other parts. It's keeping us all together here, right, in our solar system. Do each of you have plans to begin studying other celestial bodies in our solar system? I know there's a lot of conversation about, particularly moons of Jupiter and the presence of atmospheres on other celestial bodies. Are you beginning to look at the effects of sun on other celestial bodies in our solar system and what we can learn from that and how it informs our life here on Earth?
That's a great question, and we do. I do have research that have been published in terms of analyzing the solar wind effects and the coronal mass ejection effects in other planets. For example, Saturn. There was just a paper published about 2 months ago about that. And the whole idea is, my team is one of the main sources that this fields have, because we are actually analyzing all the CMEs that are going on the backside. And one of the 2 months ago, I got a call from Argentinian colleagues saying, Jerry, can you help us understand if these are the CMEs that are causing the problem, that are causing the aurora in Saturn? And then it went up into a whole paper published, and this is not the only one. We also have collaboration with Juno and the Jupiter environment, and also some of the moons between those two bodies, between Jupiter and Saturn. So, I mean, yes, we work into analyzing, understanding the space weather effects on other bodies, and I know Phil has much more to say about this.
Yes, absolutely. That's what the study of heliophysics is really studying the sun's influence on the entirety of the heliosphere that encompasses everything within its boundaries. And to channel our new NASA Associate Administrator of Science, Dr. Nikki Fox, she says that heliophysics really is the study of everywhere the sun shines, because all of these variations, especially the variations in the ultraviolet and X-rays, they really drive the energy input in all bodies within the solar system, both the natural ones and the artificial ones that we're putting out there. And I will mention, a study I've done working with a handful of other people is looking at the dust charging on the moon. So the moon doesn't have a magnetic field, so the solar photons reach the surface and it actually ionizes the dust on the moon and causes it to be charged, static charged. And this is a problem for astronauts. So if we go back to the moon, one of the biggest complaints the astronauts have is the dust sticking to their boots because of this static charge that's caused by the ultraviolet radiation from the sun. And therefore, when a solar flare goes off or you're at solar maximum, you're going to get more charging of this dust. You actually get transport of the dust. The dust moves around some as well, and it sticks to the astronaut suits. And that's not good. You don't want to be bringing dust into your lunar module or your lunar habitat. That then gets into the air. It's really fine grained, and it could be a problem. So one of the complaints that came back from astronauts that were on the surface was that dust is a big problem. So if you're going to go there long term, you're going to set up a habitat on that. Got to worry about dust charging, and that's all caused and driven by the photon output of the sun. So yes, I have studied the moon, obviously Mars, as we've talked about, and Earth. There's X-ray solar monitors going around Mercury right now on the Messenger spacecraft. If the sun is touching it, chances are I'm involved in it, and especially if we start to send human and technological assets to places, then by all means we're going to have to be involved.
Well, that is so fascinating about the photons of the sun hitting the moon and the regolith and causing it to become charged, because there's the famous story from Apollo 11 when Buzz Aldrin and Neil Armstrong were ready to leave the surface of the moon and reconnect with the module, and they had brought regolith dust into the capsule, and the switch that Buzz Aldrin was supposed to lift got stuck, and he pulled so hard it broke off. And so he actually took a pen and jammed it into the console and lifted it up, and that enabled the gases to ignite and for them to leave the surface of the moon. Otherwise, they couldn't. So, you know, it is there's a real, and I know that because we premiered the Destination Moon exhibit here on the 50th anniversary of Apollo, and we had the pen and the switch and that story. So there is evidence that that is an issue. That was nearly catastrophic for that first mission to the moon. Well, I have so enjoyed our conversation today, and we're running close to the end of our time, but I wanted to wrap up by asking if you each could share with us, how did you get into doing space weather and the science around what you do? We have a lot of young people who watch this program and are interested in different careers and exploration. And if you could just take a minute to kind of share your journey. Was there a particular experience you had at a point in your life that kind of put you on this pathway? But how did you get to where you're at today in your careers?
Yes, I wanted to be an astronaut since I was 6 years old. I have a very humble family. I'm from Puerto Rico, and we traveled to Florida, went to the Kennedy Space Center, and I fell in love with astronomy, the stars, everything that had to do with NASA. However, when I started growing up, I actually applied to do a law degree because I do like law too. But, you know, one of the things that I started to do also was doing internships. And when I started my internship here at NASA, that's when I found out about the amazing things that the sun can actually do. The sun is the one that, you know, it makes it possible for us to have life on Earth, but also the solar storms and all the things that can affect. I was like, what? So that's when I fell in love with the space weather and the heliophysics field. And then I started working in research. So my background is in the magnetospheric physics side. So I study the interactions of the solar wind with the Earth magnetic field. That's my background. But then I started doing space weather with the CCMC. They had an experimental space weather group that I actually led for many years, and I loved it. And this is definitely my calling. I love space weather and all that has to do with the effects and how it actually interacts with all the planets, the missions, the instrumentation. We work with so many people, engineers, IT people, computer scientists, you know, everybody, administrators, everything. So it's an amazing field, and you know, like Nikki Fox says, it's an amazing time to be a heliophysicist because, you know, it's a growing field, and because we're growing in our technology, you know, we depend so much in technology, and we have to protect those assets that make that technology possible. So that's why space weather now is, you know, has a lot of attention. So it's a great time to be a heliophysicist and study this field. And like I said, it is my passion, and I don't regret moving away from the law degree. I didn't start it, but I actually applied for it, and then I started physics. So, you know, that's how I fell in love with the space weather environment.
Yeah, thank you for that question. It's always a good question. I get asked a lot, and you know, it's once again, you know, I grew up with my dad. My dad's a PhD geologist. My mom's also a geologist, and so science was always, you know, a big part. Going out in the backyard and looking at the telescope, looking at the stars with them, and just always talking science and with them and having them around to just, you know, just feed and always answer my questions that I had. But similar path is that I went to an undergrad at Hanover College in Hanover, Indiana. I wanted to be a doctor. And so the first year I was there, I had a doctor's appointment, and I was like, I really hate needles, and I really can't stand blood. And finally realized probably being a doctor is not the way to go. But I was taking biology and chemistry, which were pre-med requirements at the time. I was like, you know what? I still love science. It's just getting back to, I just love science and understanding whatever science it is. And then my sophomore year, I took a physics class with Dr. Nickus there at Hanover College, and just absolutely fell in love with physics and just understanding why things work, on all aspects. Took astronomy classes there, was able to do some research. My senior research thesis, he actually had a spectrometer hooked to the local telescope. They had a campus telescope that was 100+ years old. It was hand ground lens. It was a historical artifact, but actually it was kind of thing like, oh, I got a spectrograph, hook up to this telescope, go figure it out. And I was like, this is awesome. So it's really where I really started building I like to do the science side of things, but I like to do the hands-on experimental side of things. And so that's why I came to University of Colorado and majored in aerospace engineering sciences, because it seemed like a great blend of the hardware stuff, the hands-on stuff, the instrument stuff that I liked, as well as still being able to do, the cutting edge science and look at the data and publish papers and figure things out from the science point of view. And I ended up getting a great job here my first year as a grad student with Dr. Tom Woods here at CU LASP, and working on a sounding rocket. And the sounding rockets are great. And the instruments that he's built and that we've had a chance to work on together over the past 2 decades has been awesome, because you never get bored. You get go in the lab, do hardware, get to build things, get to see things you build launch into space. But then you also get to be the first one to see that science, and you get to be the first one to discover that new thing that no one's ever found before, and publish that paper and present those results at a conference. It's a great field to be in. You don't just get to study the sun. You get to study Mars, the sun's influence on Mars, the sun's influence on the Earth, and study how it really affects us and the technology we're dependent on, which a lot of scientists can't say, how does this directly influence my day? And I can. The science that we work on, that Jari and I work on, it really impacts us on a day-to-day basis and influences humans once they're trying to go to these really cool places that no one has ever gone before. So it's awesome to be a part of the whole business, and it's exciting, and it's just a fun job.
And also for the young viewers, I will say, try many things as possible. It's okay not to know what you want to be when you're in high school. That happens. So I always tell my students, I have many students during the years as interns, and I always say, try different internships, try different positions, different fields, because you never know what is actually going to call you. Before I started at NASA doing space weather and heliophysics science, I was actually doing fire and building research lab at NIST. And I did enjoy it because I love it. I love to actually burn stuff for fun and for science, but it wasn't my calling. So when I started here, that's when I actually knew that this was my passion. And also, don't let anybody tell you that you cannot do it. When I was, growing up and trying to get to NASA, a lot of people were like, you going to NASA? I doubt it, And I turned that doubt into something that would push me to make it real, okay? So if you are actually dreaming on something, just make it happen. But it takes a lot of effort, a lot of time, a lot of sweat. But if it's your passion, you're going to feel happy every day to do it.
Thank you both for those inspirational words. And what really resounds with your comments is you're following your passions. And I always say the same to young people, follow your passion. And also, it doesn't mean it's going to be easy, but that makes it even more motivating, because when you succeed, when it's hard and you're following your passion, it's even more satisfying when you have those achievements. I want to thank you both so much, Dr. Yaresca Collado Vega and Dr. Philip Chamberlain. What a fantastic conversation today. I learned so much and am so inspired by the research that you're both doing and all the contributions you're making to human space exploration and exploration in general in science. So our heartfelt thanks to you for participating in our program today. And also, our program is possible because of the generous support of UTMB that helped make possible this series, our Thought Leaders program on space weather, the sun's influence on humans and technology. Thank you again for joining us, and check out our website at spacecenter.org to see other past programs in our Thought Leaders series.